What up? It's time for Advent Code Day 6. For part 1, we have Guard Gallivant. They give us a map. It shows our current position with a caret to represent that the guard's facing up. And then any obstructions are represented with a hashtag, and then these dots represent empty spaces. The guard follows a strict protocol. If there's something directly in front of the guard, they turn 90 degrees right, and otherwise they take a step forward. If we follow the guard, we see it steps forward until it reaches this obstacle right here. Then it turns 90 degrees right, steps forward until it reaches this obstacle, and so on. So we're asked, how many distinct positions will the guard visit before leaving the mapped area? So let's look at our puzzle input. You can see here that I saved the input to this text file, and I also put a test one so that, and they're right next to our script that we're going to work on. So first, let's get our input. Let's parse it. We can get our grid by just taking each line and making sure we remove the new line at the end with our strip in our file. And then we can pass this into part 1. So let's print the grid. Make sure that it looks the way we expect. Let's do it for our test one so it's easier to see if we did it correctly. And we can see we have each row in the list. So now, how to approach part 1? We should just directly simulate how the guard will move. Because we know he won't get stuck in a loop. He'll only visit each position a finite number of times, and there's actually only so many positions here. Maybe like a couple thousand at the worst. So how do we actually simulate his movement? The idea I had during the competition, and that worked pretty well, was that we could just represent his direction with a complex number. So in the beginning, he's moving up, and so we could represent that with -1 because he's moving down the rows. And then each time he turns, we can multiply by -1i to represent a clockwise rotation. And that makes handling the directions a lot easier because the direction is sort of encoded in how complex numbers work. So let's try it out, right? First, let's get our grid dimensions. Then let's get our starting position. We'll obtain that by looking at each position in the grid and only choosing it if it has the value of the caret. So let's say for I in range M, for J in range N, but only if grid at I, J equals caret. Then we'll initialize our simulation. Our starting position will be the start, so that'll be I and J. Our starting direction will be -1. That'll be clear later. And we'll maintain a set of visited positions. So I'm going to have this while true loop, which is just going to run while we simulate our guard's steps. The first step that we'll do in this loop is that we'll add the current position to the positions that we've visited. Then we will try to advance the guard, but first we need to make sure that when we advance it, he's not going to run into an obstacle or out of bounds. So we know he'll never need to turn more than 4 times because there's only 4 directions. So we'll bound the number of times he can turn by 4, and then we'll look at the next I and the next j. And the way that we'll obtain the next I and the next j is by taking the real and imaginary components of our direction. As follows, we'll say I plus equals direction dot real, and j gets direction dot imaginary. Just like that. And now we see why I chose -1 is because initially we want the guard to be walking upwards, which means that he should be going down the rows. So the real part should be negative, and then since he shouldn't move horizontally at all, the imaginary part should be 0. Right? And so when he steps forward, he steps out of bounds, that means we're done, and we should return how many positions we've visited. So if ni is not in bounds, or and j is not in bounds, then we should return the length of visited. And if he steps forward and the position is blocked, so if it's a obstruction, which was the hashtag symbol, then we should turn clockwise 90 degrees. And so when you multiply by the imaginary unit, you turn 90 degrees counterclockwise. Since we want to go clockwise, we should return by the negative of the imaginary unit. And so in Python, you represent that with j. So I'll say direction times equals -1j. And then otherwise, that means the step forward was just fine and we should break. We shouldn't continue to churn, right? Lastly, we should update our current position to the next position. And so if this worked properly, when we run this on the test, we should get 41 distinct positions on our map. And if we switch it to the input, we got 5,208, which was the answer for part 1. For part 2, they tell us that they're pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place a new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. So, the historians would like to know all the possible positions for such an obstruction. How many different positions could you choose for this obstruction such that it will get the guard stuck in a loop? How can we approach this part 2? We can try simply placing obstruction in every position where there isn't one and seeing if when we simulate, we end up getting caught in a loop. We can reuse a lot of this code from part 1 for part 2. I'm going to factor out the simulation into a step that checks if the grid has a cycle. So I'm going to make a function called hasCycle, and it's going to take in the grid, the starting position, and the obstruction that we introduced. And then we're going to reuse most of this code from part 1. The main difference is going to be that when we keep track of the places that we visited, we're also going to make sure that we keep track of the direction that we're facing. We'll know that we're caught in a loop if we visit the same place facing the same direction. And instead of returning length of visited, what we should return is that we're not in a loop. Otherwise, if ij direction, so the current state that we're in, is in visited, we should return true, that we are in a loop. And lastly, we should not only check that ni and j is equal to hashtag to see if there's an obstruction, but we should also check that ni and j doesn't equal the new obstruction. So it can be either of these conditions. Now that we have our function has cycle to determine whether introducing an obstruction makes the guard walk in a cycle, we can do part 2 and it'll be pretty short. So let's take this first part of part 1, where we get the dimensions in the start, and bring that down to part 2. And what we'll do is we'll keep track of the number of obstructions that we could put that introduce a cycle. So we'll say num cycles equals 0, and at the end we'll return the number of cycles. And what we want to do is we want to look at every position in the grid. And if introducing an obstruction at that position introduces a cycle, then we should add 1 to num cycles. Just like this. And one easy thing that we can do here is we can only put obstructions where the grid is empty, right? So if grid of j isn't a period, then we should skip it, because it's not worth putting an obstruction there, because there's either already an obstruction there or the guard is there in the first place. If we run this in our test input, let's see if we get the expected result, which was 6. It's correct. And let's run it on our regular input. And we get 19 to 72, which was the answer for part 2. One more thing to note is that part 2 actually took a long time to run. Let's time it, right? I'm going to say start equals time dot perf counter, and then I'm going to print time dot perf counter minus start. So this will represent how much time was between before we started part 2 and when part 2 ended. And I'm going to run it again. And you can see it took over 30 seconds. So is there a way that we can cut down on that time? Well, one thing we can do is look at the places where we could add obstruction more intelligently, right? So one thing we might notice is that, hey, if a point isn't in the path that the guard initially takes without any new obstructions, then adding an obstruction there won't be worth it, because the guard will never visit that point and have his path be affected by it. So instead of looking at every possible position to put an obstruction, we should only look at the positions that were initially in the guard's path. So one way we could get this to run a little faster is to get a result from part 1 besides the length of visited. We could alter part 1 to simply give us every element that the guard visited, like this. We could say visited equal part 1 of grid, and then to get the answer we would just print the length of visited. And then for part 2, we'll pass in visited along with the grid, right? So down here, in my definition, I'm going to add a visited parameter. And then I should only look at for I and j in visited. And now when we run it, we see we only get about 7 seconds instead of 30. Thanks for watching. Hope you liked my approach with the complex numbers. If you want to solve LeetCode with me on the daily, come join my Discord. I have the link in the description. And yeah, have a good one.